stable, which one is less stable. Then comes your aromatic compound, anti-aromatic compound, and non-aromatic compound. Then comes your hyperconjugation, then bond length and bond length. Which one is larger bond length and which one is having shorter bond length. Basically, relative bond length or bond energy concept. And then again, stability of carbocation and then carbon anion, and also at last we will discuss about acids and bases. Which one is more acid and which one is less acidic. So let's start this. Basically, there is a concept that is called electronic displacement effect. Basically, it is about the displacement of electron, the movement of electron. Where does electron go? That effect is called electronic displacement effect, and it is of two types. The first one is permanent effect, and the second one is temporary effect. That means basically, you can take an example from physics. There are some substances which will come in contact with magnet, and they will behave as a magnet for a while, and then it loses its magnetic property. That is temporary. And there are some substances which will be in contact with magnet, and they will hold the magnetic character for the rest of their life. That is called permanent. So basically, there is permanent effect, and in this permanent effect, we have three topics. That is inductive effect. One by one, we are going to study about this inductive effect, mesomeric effect or resonance effect, you can say, hyperconjugation, and the temporary effect, inductomeric effect, and then electromeric effect. So we don't need to study about this. These are temporary effects, but we need to study deeply about this three, because this three is very, very important. So first of all, I'm going to start this inductive effect. So what is this inductive effect? First of all, this is your permanent effect, and it arises due to electronegativity. So as you know that there is CH3Cl. There is a compound that is chloromethane, and you know that the more electronegative element here is chlorine and less electronegative is carbon. So what will chlorine? Carbon's electron towards itself. So there will be delta negative charge and there will be delta positive charge on this carbon. And this effect is basically called inductive effect. This inductive effect operates through sigma bond, not pi bond. It will act only in sigma bond, and it is distance dependent effect. Let me show you an example, and with this I can easily explain. See, this is your CH3 CH2Cl. Now you can see this is more electronegative, so there will be delta negative, and this will be your delta positive 1, then delta positive 2, then delta positive 3. So basically, this is the inductive effect which operates through sigma bond, because this chlorine is more powerful, having more powerful electronegativity. So it will directly not withdraw, it will directly displace carbon's electron towards itself, then from this carbon, then from this carbon. It is also very important to note that inductive effect is inversely proportional to inductive effect is inversely proportional to distance. That means basically you can see chlorine can displace electron more powerfully with the first carbon as compared to the second carbon, and then third carbon, and then the fourth carbon. It has been found experimentally that after third carbon, inductive effect, the effect of inductive effect is diminished, or it is almost zero. Is that clear to everyone?
Yes,
Clear?
Yes, sir.
Okay. So basically, two things here is very important. That is, it arises due to electronegativity proportional to distance. The substances where electronegativity difference is more, that means there is more inductive effect. Now I have written some points. Whatever I told you here, I'm just going to read it. If you will have any doubt, just ask me. Causes of inductive effect is electronegativity difference. Inductive effect is permanent effect. It is weak effect. Basically, it is weak effect because it has partial transfer of sigma bond electron. Since it operates through sigma bond, so we can call it sigma electron. So you know that there is HCl. I'm going to show you. This is your HF, and you know that this is fluorine, which is most electronegative element. So what it will do, it will withdraw, not withdraw basically, it will displace hydrogen's electron towards itself. So it will have delta negative, this will have delta positive. You have seen in ionic compound that complete transfer of electron takes place. That's why their charges are discrete, or it has been shown that like Na plus Cl minus. That means sodium totally loses one electron. That's why plus one, total plus one charge. And here chlorine totally gains one electron from sodium. That's why negative. And here you can see delta negative and delta positive. So basically the electron of hydrogen is in its orbital. It will be in 1s1, but slightly displaced towards the fluorine. That's why delta positive charge. Inductive effect is inversely proportional to this. After third carbon, inductive effect is considered as negligible, and also inductive effect of hydrogen is considered as zero. This is also very important. The inductive effect of hydrogen, we consider it as zero. After this class, you will get the PDF of this. So if you want to write it, I will recommend you to write only question, do only question. The theoretical part you will get after class. Okay. Now see, inductive effect is of two types. Inductive effect is of two types, plus I and minus I. Plus I, that means the group which donates electron, or the group which will have lesser electronegativity, and the minus I is the one which withdraw electrons, or which have more electronegativity. So you can see this is also very important. In general, alkyl group has plus I effect, whether it is methyl, ethyl, propyl, butyl, pentyl, it will have plus I effect. That means it will donate electron. Now there is a very basic question on this, that is find the inductive effect of encircled group. What you need to do, just see the fluorine and see the attached compound or attached element to which it is attached, and let me know fluorine will show minus I or plus I. Can anyone tell me? Minus I. It will show minus I because fluorine is more electronegative than carbon. That's why it is minus I. Priya, what about this? The second one. What do you think?
Plus I.
Plus I. Is there anyone? Plus I. Adriel, Hamza. See, this will show minus I. I will explain why it is so. You have studied in previous class that carbon having sp hybridization will be more electronegative than carbon having sp2 hybridization. This is your electronegativity order for the carbon having sp hybridization, sp2 hybridization, and sp3 hybridization. So if you are going to calculate the hybridization of this carbon, this will be your sp2, and this carbon will be having the hybridization sp3. So this carbon will be more electronegative. That's why it will act as minus I. Is that clear? Aditya, Priya, Hamza, Adriel?
Yes, sir.
Priya, have you got it?
Yes, sir.
Okay. Can anyone tell me what about this CHO? Will it show negative or positive? Plus I or minus I? See, what you need to think is, what about this carbon? This carbon, there is also carbon. Very good. That's the correct answer. This is your sp2, same carbon, and this is also your sp2. but still this will show minus I because this carbon is connected to a second most electronegative element, oxygen. So this oxygen will withdraw electron from this carbon, and that's why there will be deficiency of electron on this carbon. And since there will be deficiency or hunger of this carbon, that's why it will act as minus I. See, both the carbons are same, both the elements are same, that is carbon having same hybridization sp2, but this carbon is connected with oxygen, which is second most electronegative element. So that will continuously take or withdraw or displace electron from carbon towards itself. That's why there will be deficiency of electron on this carbon, and hence it will be that's why it will attract electron from here or withdraw electron from here or displaces electron from here. That's why the CHO will act as minus I. Is that clear, everyone? What about this OH? It will show minus I because this is your carbon and this is your oxygen, second most electronegative element. Now see, this is your CH3 and this is your carbon. This is your carbon, this is also your carbon, but this is your sp2 and this is your sp3. So it will show plus I. sp3 carbon is less electronegative than sp2 carbon. Is that clear, everyone?
Yes, sir.
Now see, what about this? Think about this carbon and this
Plus I.
carbon. Sp and this is your sp2. Very good. This will act as plus I. What about this carbon? What about this carbon? Can anyone tell me? See, this carbon is your sp2. This carbon is your sp2, and the group which is attached with this carbon is also sp2 and sp2. So basically, there is no electronegativity difference. So there is no inductive effect. Is that clear? If there will be no electronegativity difference, that's why there is no inductive effect in this compound. Is that clear, everyone?
Yes.
Yes, sir.
Okay. So I'm gonna ask you a question about this. Can anyone tell me? Here I'm going to write. Will there be any inductive effect in this compound? Yes or no?
No, sir.
No, there is no inductive effect because you can see this is also carbon. First, you need to check the elements carbon, carbon. And then if you are going to check the hybridization, each and every carbon here is sp3 hybridized. So there is no inductive effect in this compound. So it is not necessary that every compound will have inductive effect. It may be or may not be, that depends upon the group which it is attached to it. Now, since I told you inductive effect is of two types, minus I and plus I. So this is the series which will be used to solve the question. So basically this minus I, that means electron withdrawing group. You can write electron withdrawing group. I can write it EWG and you will understand. This is the short form that I am going to use, EWG, electron withdrawing group. So the group which is having the most powerful withdrawing power, that is NF3 plus, NR3 plus, NH3 plus, NO2 plus, CN minus, that is CN, fluorine, chlorine, bromine, iodine. The most important thing that you need to know is this alkyne is more electronegative than NH2. This alkyne, basically the carbon which is having sp hybridization will be more electronegative than the nitrogen which will be sp3 hybridized. And then comes your benzene, and then comes your alkene, and after that hydrogen. And for hydrogen we consider ionization in inductive effect as 0. So I will recommend you to, if you want to write it, these are very important. Can I move to the next part? Everyone done with this? Adriel, are you there?
Yes, sir.
Okay. I'm going to change the slide. Can I change the slide? Everyone done with this?
Yes, sir.
Yes, sir.
Then comes your plus I series. That means electron donating group. Electron donating group. So the most donating group, which is having CH2 minus, NH minus, O minus, C double bond O minus. Then comes tertiary alkyl. That means CH1, which is directly your CH2, not CH2, CH3 here, and this is your CH, and then it is connected with another CH. And then comes your 1 degree. So this is your 1 degree. So everyone knows what is the degree of carbon, how we calculate degree of carbon. If you are going to calculate the degree of any carbon, just look at and see to how many carbon it is directly attached. Like to calculate the degree of this carbon, you can see it is directly attached with 3 carbon. That's why I wrote here 3 degree, and it is for this carbon. If you are going to calculate the degree of this carbon, it is attached with only 1 carbon. That's why its degree will be 1. So this is how we calculate the degree of carbon. Also, it's very important to note that this is your C, that means tritium, deuterium, and hydrogen. In this, it is isotopes of hydrogen, and in this 3, tritium has the more power to donate electrons as compared to deuterium and hydrogen. Is that clear? Can I
Yes.
change the slide? Okay.
Yes, sir.
Thank you. Thank you, everyone. Now, we are going to discuss about the application of inductive effect and what is the application of inductive effect. So basically, first of all, we are going to discuss about the intermediate. What is intermediate? Basically, if you are going to do a reaction like this, and your final product is C. So what I want to say is that if you want to prepare reactant for another reaction. Are you getting my point? You have seen this intermediate. Intermediate is the one which is product for a reaction and reactant for another reaction. That is called intermediate. Is that clear? There are a lot of reactions that proceed through intermediate. We will be going through intermediate. Is that clear?
Sir,
Yes.
could you repeat? You were stuck for a bit.
Okay. So Adriel, you can see what is intermediate. Species, which is product for one reaction and a reactant for other. You need to go through B. So this B will be acting as intermediate, and this B is product for A and reactant for C. Is that clear? Basically, in reaction, in organic reaction, you will be seeing the intermediate as carbocation, carbon free radical, carbon anion, and all. So before getting the main product, you will be going through some intermediate, and intermediate is the one which will act as product for a reaction and reactant for another reaction. Adriel, is that clear?
Yes, sir. Thank you.
Okay. Now, this is very important. Do you know fission? You know that fission is bond breaking. Here in chemistry, we will talk about bond breaking or bond cleavage. And bond cleavage can be done by 3 different ways. The first one is I'm going to take is, oh, wait a minute. Okay, let's do this. So the first one is heterolytic. 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 So what is this heterolytic means? Heterolytic, that means one of the atom or one of the element will take electron from another and it will be out like this. Chlorine will take electron from carbon. Chlorine will take electron from carbon. So it will be Cl negative, and this carbon will have positive charge since it donated its electron to carbon. So this is what heterolytic looks like. That means more electronegative elements will take electron from less electronegative elements, and it's heterolytic. One element will gain full electron of the bond or complete electron of the bond, and this bond or this fission is called heterolytic. Now we are going to talk about the hybridization of this C plus. Basically, whenever there will be positive charge on carbon, that is known as carbocation. That is known as carbocation, and you can see only 3 sigma bond, no lone pair. So hybridization is sp2, and for hybridization sp2, we will have trigonal planar. The geometry is trigonal planar. Now, if you can see, what about octet? Octet is incomplete since it is making only 3 bonds and there is no lone pair. So 3 bond, that means 3 into 2, 6 electron. That means incomplete octet. Incomplete octet. Is that clear? Is that clear, everyone? Heterolytic, heterolytic cleavage or heterolytic fission. That means one of the elements will take electron from another. That's why there will be negative charge, and since the one which donated will have positive charge on that. So carbon, whenever having positive charge, that is known as carbocation, which will have incomplete octet, having sp2 hybridization and trigonal planar. Now, I'm going to cleave it like this. Carbon took electron from, wait a minute, since it is, we are going to talk about free radical. In free radical, this is your homolytic cleavage. Homolytic cleavage. You know that in covalent bond, there is equal sharing of electrons. One electron will of mine will be shared with one electron of yours. And in homolytic cleavage, or for every element will take its own electron. You can see in one bond there is 2 electrons. So carbon will have its own electron, CH3, and there will be Cl dot. Now you can also see that whenever there will be one dot or one electron on carbon, that is known as carbon free radical. What about octet? You can see carbon is making 3 bond with hydrogen, that means 6 electrons, and 1 unpaired electron, that's why 7 electrons. It is also incomplete. Octet is incomplete. Now, if you are going for hybridization, it will have sp2, and geometry, it will have trigonal planar. Trigonal planar. Now going for carbon anion. Carbon anion, that means carbon will have negative charge. So I'm going to break it like this. Carbon will gain electron from chlorine, so it will have negative charge, and chlorine will have positive charge. Fission, you electron from the bond, that's why it is heterolytic. That's why it is heterolytic. Now what about hybridization? There is negative charge, that means that will act as lone pair, making 3 sigma bond plus 1 lone pair, that is sp3. 3 sigma bond plus 1 lone pair, that means sp3. What about octet? You can see 3 sigma bond 6 electron and 1 negative charge, that means 2 more electrons, so it is 8 electron complete octet. Octet is complete. And here you can see geometry. Geometry will be trigonal pyramidal, not tetrahedral. Do not go for tetrahedral because it has 1 negative charge which will act as lone pair. So having 3 sigma bond, 1 lone pair, that is trigonal pyramidal. The structure or the geometry will be like NH3. Is that clear, everyone? So this is your carbon free radical, carbon anion, carbocation. That means positive charge on carbon, positive charge on carbon. And for preparing or producing carbocation, you have to do heterolytic fission. You have to do heterolytic fission. That means one of the group which is attached with carbon will take electron from the carbon and make it positive, and there will be negative charge on that. What is carbon free radical? It will take its own electron, and the electron will be divided equally, and there will be a dot or a free electron on carbon, that is free radical, and it will be done by homolytic cleavage or homolytic fusion. And carbon anion, that means negative charge on carbon. Carbon will take electrons from a group. There will be negative charge, that is known as carbon anion. Is that clear, everyone?
Yes, sir.
Okay. Can I change the slide?
Yes, sir.
Okay. Now see, you need to do this question since you have passed class 12. I hope you can do this. So please do this question. I'm waiting. I'm giving you only 1, 2, 3. 3 question is there. So you just need to arrange. Wait a minute. Let me show you. This is your A. This is your B. This is your C. And this is your D. And you need to do it in decreasing order. So this is your A and this is your B. You have 1 minute to do this. This is your C. You have 1 minute to do this question. Please do it. If anyone facing problem, please do let me know. I will be explaining again. Alkyl group has plus IF. How we are going to solve it? It's very easy. Now I'm going to show you. Have anyone done this? Aditya, Vedarsni?
Yes, sir.
Yeah. So in the first,
Sir, I've done those.
okay. Vedarsni. A, B, C, D. A is the most stable, right? Very good. And here comes Aditya, A, B, C, D. But I can't see the third. Yeah, I know that. Okay. Okay, see. I'm going to explain it. And in A, B, C, D. Very good. Now, see, I'm going to explain the first one first. Okay. You can see you have to find a common point in between these compounds, and you can see there is positive charge. That means it is carbocation, which will have incomplete octet, and every element in this universe wants to be stable by completing its octet. So this carbon is gaining two basically support from this side, or this. Or you can say this is your 3 degree and this is your 2 degree. This is gaining support from two sides, and this is gaining support from one side, and there is no support. That's why. Oh, very good. You have seven that comes up. So basically, this will be your answer. A, B, C, D. The most stable A, then B, then C, then D. Now, when we are going to talk about this NO2. NO2. See, first of all, there is a very easy trick to calculate. Whenever there will be positive charge will be stabilized by positive. This is, you need to keep it in mind. Positive stabilized by positive. That means basically there is positive charge, and positive, that means plus I. So cation, carbocation having positive will be stabilized by plus I. The group which is having more plus I will be more stable. Now you can see this has a nature minus I. This has a nature minus I. This also a nature minus I. Reverse is also true. Positive charge, whereas NO2 is very nearer to this carbocation, it will destabilize this carbocation because this carbocation is in needs of electron, but this NO2 will withdraw electron from that carbon. And since it is nearer to this carbocation, it will withdraw with more powerful as compared to this NO2, and then with this NO2. This NO2 is far away from both the A and B. That's why the more stable will be like this. So you can remember it like this. Positive will be stabilized by positive. Positive will be destabilized by negative. Or you can also do it like this. Negative will stabilize by negative. Is that clear? Can I change the slide? Okay. This is the concept. Now you can see all are same. Only the difference is there is CS3, there is CD3, there is CT3. So I already told you to donate. C is the most donating group, then D, then H. That's why this will be the order, because this positive carbocation will be in need of electron, and tritium can donate easily more than hydrogen and deuterium, and deuterium can donate easily more than hydrogen. Now this is the fourth question in which DNP rule applies. DNP. D for distance. D for distance. We will, and then number, and then power. And deficiency of electron. There is deficiency of electron, and there is a fluorine which is just near to this carbocation, and there is NO2. Both will have minus I effect. Both will have minus I effect. Since NO2 is farther away from this carbocation, that's why its power decreases, and hence it is more stable. Fluorine is nearer, so it will withdraw electron or displaces electron of this carbocation more easily than this. That's why NO2, this is more stable. And here, like this, number and power. You can see 2 chlorine will have more, will be having more power than 1 NO2. That's why this will be the stability order. So whenever you are going to calculate the stability order, what you need to do, just find a common point and think about which will stabilize it and which will destabilize it. Since in the last question, you can see fourth question, there is positive, that means plus I will stabilize it and minus I will destabilize it. But here in both the question, minus I is there. Now think about which group will take or withdraw lesser electron. This one. So that's why it is more stable, because the distance increases, and you know that inductive effect inversely proportional to distance. That's why it is more stable. And here you can see distance is same, but the number of groups is greater. So 2 chlorine will have more withdrawing power than 1 NO2. Is that clear? Is that clear?
Yes, sir.
Can I change the slide?
Yes, sir.
Yes, sir.
Wait a minute. I'm having. Okay. Now, the next topic is resonance. What is resonance? You can see complete transfer of pi electron. You have to be careful. What is inductive effect? Inductive effect operates to sigma bond, and there will be partial displacement of electron. It will not be out from its orbital. There will be only partial displacement. But when we talk about resonance, there will be complete transfer of pi electron, not sigma electron. First of all, pi electron, and then transfer of pi electron. That means it will move from one pi electron will move from one atom to another atom. Another important point to remember is that in resonance, atom does not move, only pi electron moves. So complete transfer of pi electron, then comes delocalization of pi electron, then comes resonating structure. When we will draw, you have seen the resonating structure. The resonating structure are hypothetical, but resonance hybrid. What is resonance hybrid? Oh, wait a minute. Resonance are hybrid. Resonance hybrid is real. What I want to say is that this resonance hybrid drawn with the help of all the resonating structure, and this resonance hybrid is real. Okay, and I have also written here that in resonance only pi electron moves, atom does not move, and also in resonance number of electron and charges always conserved in each resonating structure. So whenever you have you will see any resonating structure, if you want to check it whether it is resonating structure of each other or not, so you just need to calculate the total number of carbon in each resonating structure. If they are equal, then it will be resonating structure. And you also need to calculate the charge. Overall charge will be same for each resonating structure. Is that clear? Can I change the slide?
Yes, sir.
Okay. Now, for resonance, system should be in conjugation. Now, how will we know where the resonance is taking place, where we can draw the resonating structure or not? So, this is the system for pi sigma sigma. Oh, sorry, you can see pi sigma pi, pi sigma vacant orbital, pi sigma negative charge, or more electron, pi sigma lone pair, pi sigma free radical, or negative charge sigma vacant orbital positive, or lone pair sigma positive charge, that means vacant orbital. If in a compound, this conjugation, if you are going to get it, then there will be resonance. Pi sigma pi, pi sigma vacant orbital, pi sigma negative charge, pi sigma lone pair, pi sigma free radical, or negative sigma positive, lone pair sigma positive. Positive, that means vacant orbital. So this is the if you are getting any conjugation, any one of this conjugation in a compound, then there will be a resonance. Is that clear? Can I change the slide? You will be getting this. Can I change the slide?
Yes.
Yes, sir.
Okay, thank you. Now, there are some arrows that is used, and you need to know symbols used to draw resonating structure. This is heterolytic fission that shows from one atom the electron from that atom will go to the another. So this is your heterolytic fission, and this shows the transfer of two electrons to a single atom. This is homolytic, that means transfer of one electron or equally transfer to its atom. And this is the arrow, double-headed arrow that we used in two resonating structure. Is that clear? And you know that the most important point here is flow of electron. You know, from higher potential to lower potential electron flow, current flows, right? Where current flows from higher potential to lower potential, always remember that resonance will also do in the same manner, like from higher potential of charge to lower potential of charge. And here, higher potential of charge is negative, then lone pair, then pi bond, and then comes your vacant orbital. So this is your higher potential to lower potential, and this is how electron goes negative to lone pair. This is the lowest, then lowest, then lowest. Is that clear? Please do respond. Is that clear?
Yes, sir.
Now I'm going to show you resonating structure of all this. First case, I took pi sigma positive. So you can see this is lower potential and this is having higher potential, pi and then positive. So the movement of electron will start from higher to lower. That means it will go like this. You can see this. Wait a minute. Let me switch off the. This. Okay. Now you can see this is your pi bond, which is having two electrons. So this bond will break and it will go to this. So this is the double-headed arrow that we use in between two resonating effects. The rest part will be as it is. Now you can see there is single bond. Now this double bond will be transferred, or pi electron will be transferred here, and the positive charge comes at this carbon since it loses its electron, and the rest part will be as it is. Don't do anything with the rest part. Now this will move to this part, and you can see this double bond will be like this. This was like this, and this, and the positive charge will be again. Now you can see double bond comes here. This part was as it is, and the positive charge is here. Now you can see. So if you know, wait a minute, I just do something there. If you know where the electron flows takes place, you can easily do the resonating structure. You can easily write the resonating structure. And now you can see in the first one, the double bond was on the right hand side here and here, and single bond was a double bond is here. But in this, it is a reverse. And if you want to calculate the resonance hybrid, it is basically total contribution of all the resonating aspects. So resonance hybrid is like this. Wherever this double bond goes or travel, you need to do double bond first was there, then you can do this. Double bond first was there, then move to here, and then there, and then like this. Now delta positive, you just need to represent with delta positive. Wherever was the positive charge, then here, and there is delta positive here, then here delta positive here, then delta positive here. There was no charge on this position. That is called meta. You know that what is meta or to parameta. Have you studied it in class 12? If you have a benzene, and if you are watching with respect to this, so this is your ortho, this is your meta, and this is your para. So this is your resonance hybrid. And that's why, due to this resonance hybrid, we also write resonance structure of benzene like this. Is that clear? Please do write it if you want to. Can I change the slide? Take your time. If you have any doubt in this, please ask me. Can I change the slide? Done, sir. Thank you. Okay. Now, moving to the next, you can see this is your case 2, which is or home mode. You need to do it at home. Just write it. Please do write it, the first one and the second one. Are you done with this?
Yes, sir.
Okay. Now the next conjugation, case 3, that I took is in conjugation pi sigma pi. So you can see it's very easy. This pi will move to this position. This pi will move to this position. This pi will move to this position. So you can easily draw it in a single line that this pi will move to this, and hence the resonance hybrid that you can draw is like this. Is that clear? Please do write. And now you can see this is more electronegative element, so it will take electrons from here. So the rest part will be as it is. But since this carbon donated electron, so it will have positive charge and this will have negative. Now you can see pi sigma vacant orbital. So this will move to this position and it will be like CH2. And since this carbon donated electron, so it will have positive charge and then CH, double bond, CH, and then O negative. And if you want to draw the resonance hybrid, you just need to show the sigma bond, rest part will be as it is. First, the double bond was here, then comes here, and there was also a double bond. There was delta negative, then there was delta positive, and then here is delta positive. So this is your resonance hybrid. Sorry, I got disconnected. Everyone done with this? Please do respond.
Yes.
Okay. Now the case 4 comes. You can see this is the case 4 in which pi, sigma, and free radical. Whenever free radical will come, you need to do the homolytic cleavage like this. And what you need to do, CH2, this will be free radical now, and there will be a free radical, and there was a free radical already, and there was a sigma bond. So this will make a bond with each other. So this is your resonating aspect. Is that clear? Now, the next one is d orbital resonance. D orbital resonance. We know that chlorine has vacant d orbital. So it will easily take electron from here. and it will be CH2 double bond Cl positive. Since d or vacant d orbital is here, so it can easily accept electron, but there will be no resonance in fluorine because there is no vacant d orbital, no vacant orbital. You can 2d does not exist. So chlorine show vacant d orbital rather. Is that clear? This d orbital resonance is very important. Can I change the slide?
Yes.
Okay. Now, rules for stability. Whenever resonating structure is given, RS stands for resonating structure, and you need to arrange them in increasing or decreasing order of stability. You need to go through this. First, you need to check the pi bond. The resonating structure which will have more pi bonds will be more stable. Then octet. If this fails, then comes to the second point. Then check the octet. If octet complete resonating structure, basically octet complete resonating structure will be more stable. Then if there is neutral resonating structure, that will be more stable than charged resonating structure. Always remember this point. Negative charge on more electronegative element is more stable, and positive charge on less electronegative element is more stable. Is that clear? And if the fifth one is opposite charge on more opposite charge nearer is more stable than same charge nearer. That means if in a resonating structure opposite charges are nearer, that will be more stable. And if the charges are similar, there should be gap between them. They should be far away from each other. And at last you will check inductive effect like the stability which is. So this is the priority order of this: first, second, third, fourth, fifth, sixth. I have written this in this way. So these all 6 points are very important for checking the stability of resonating structure. Is that clear? Can I change the slide? Hamza, Priya.
Yes, sir.
Okay. Now you need to do this question. This is very easy, and I have given 5 questions in this. You have 3 minutes. You have 3 minutes for this question. You need to do like A and B. Your A, this is your B. This is your A, this is your B. And then this is your A, this is your B. This is your A, this is your B. You have 2 minutes, not 3 minutes. Any answer for the first one? You need to check the pi bond. You can see pi bond is here 1 and pi bond is 0. So this will be more stable. Now you can see negative charge on more electronegative element is more stable. Now you can see this is neutral, this is charged, so neutral is more stable than the charged resonating structure. Now these are equal because they are identical. So these are equal, they will have equal stability. Now come to this. same almost. So go for inductive effect. This this is 1 degree and this is 2 degree. That's why this is more of it. It was so easy. Is there any doubt in this file? Priya, Hamza, Adriel, Aditya. Everyone done with this? Can I change the slide?
Yes, sir.
Yes, sir.
Okay. Now we are going for mesomeric effect. Basically, the effect of resonance that is called mesomeric effect. So mesomeric effect is of two types, plus M again, the one which donate electron, and the one which withdraw electron will be denoted by minus M. This is very important. Okay, plus M and minus M is same as resonance. Electron donating group via resonance, that is called mesomeric effect. Electron donating group or electron withdrawing group via resonance, that is negative mesomeric effect. Negative mesomeric effect. Now you can see I have given this. So this is lone pair, so it will donate. That's why this will be acting as plus. And this is doubly bonded oxygen, so it will withdraw electron from the ring. That's why this CHO will be acting as minus M. You need to know what is the effect of each group, whether which one will act as plus M or minus M. This is important. Like the way we did in previous one, inductive effect, you need to do the same. What do you think? This oxygen will acting as negative or positive, plus M or minus M. Always remember that when oxygen is singly bonded, it will act as plus M, and when oxygen is doubly bonded, it will act as minus M. So this is singly bonded, so it will donate. That's why plus M. This nitrogen is also singly bonded, and there is lone pair, so this will be also acting as plus M. Now you can see chlorine has a lone pair, so it will also start donating, and there will be plus. It is also important to do inductive effect as well with this. So this will plus M, but if you are going to check for inductive effect, it will have minus M. Sorry, minus I, because oxygen is more electronegative than carbon. Again, this nitrogen will be NH2 will be acting as minus, and chlorine is plus M, and here minus M. Always remember that this mesomeric effect will have more priority. We will give more priority to mesomeric effect than inductive effect. So the mesomeric effect here will be more than minus I. Minus plus M will be more than minus I. Plus M will be more than minus I. And here for X halogen, the minus I, that means inductive effect, will be greater than mesomeric effect. And this is very important. Whenever you will see that mesomeric effect is more than inductive effect. But here in chlorine case of chlorine, the inductive effect is more than this. And here you can see there is no resonance, only minus I, because there is no conjugation. You can see lone pair sigma sigma. If there will be pi bond, lone pair sigma pi, then there will be conjugation, and then there will be resonance, but there is no resonating effect, resonance effect. Is that clear? Can I change the slide? Just let me know. Let me know when you are done.
Done, sir.
Now you can see this will have minus M effect because oxygen is connected with double bond. So it will be like this, and nitrogen is more electronegative element, minus. Again, you can see CH3. There is only plus I. There is no resonance here. And here O negative, so it will donate. So it will be acting as plus. C double bond O, that's why minus M, and also you can see minus I as well. We already discussed about this, why it will show minus I effect. So you can see that. Let me know when to change the slide. Can I change the slide? Please do
Yes,
this.
sir.
Now, I'm going to draw a resonating structure of this OH that will show plus N, and CHO that is a problem in aromatic compound. So you can see this will withdraw, this will donate electron. Wait a minute, just let me change the color. And this will be moving like this. So what will be here? It will be negative, then comes double bond, and there will be positive one. And the rest part will be as it is. Now the negative charge moves to here, double bond comes here, double bond, and then OH positive. Again, this will move to this, and this will move to this. So the double bond comes here, negative charge will be here. Oh, wait a minute. This double bond. Wait a minute. This will move to here. Negative charge will be here. Now the double bond is here. You can see like this. So can anyone tell me with respect to this OH group? Now OH is here as it is. With respect to this OH group, OH plus group, the first negative charge is on what position? Ortho, and then para, and then again ortho. There is no charge on meta. There is no charge on meta. So when you are going to study electrophilic substitution reaction, aromatic electrophilic substitution reaction, that means basically when E plus electrophile, everyone knows that electrophile is the one which is having deficiency of electron. So if this E plus wants to attack, on which position it will attack? Either it will attack ortho, either it will attack para. Because on ortho and para, there is negative charge. That means more electron density is there. There is more electron, and this electrophile is in need of electron. That's why it will always attack on ortho and para, not meta. And that's why this plus M, this group which is acting as plus M, will be known as ortho-para directing, because due to this plus M, there is negative charge on ortho and para, and on meta this is neutral. So on which position this electrophile will wants to attack? Ortho and para. That's why plus M is also known as ortho-para directing. And this, due to this plus M, there will be electron density increases. The electron density in benzene ring will increase because it started donating electron. Is that clear, everyone? Since electron is donating by this OH, so electron density will increase in ring. And ortho-para directing, because there will be negative charge on ortho and para. Is that clear, everyone? Please do
Yes,
speak
sir.
up. Okay, now see this CHO, it will attract electron, it will take electron. So since it is acting at -I, electron density will decrease. Electron density decreases. It is withdrawing electron from a ring. That's the electron density decrease. Now there will be positive charge, and then there will be double bond, and then there will be O negative like this, and the rest part will be as it is. Now you are going to move this, and the positive charge will be here, and double bond here, double bond here, double bond CO negative. Now this will move to this. Now you can see the double bond will move to this. Now there was double bond, positive charge is here, double bond is here, CO negative. Now what will happen? This will move to this. At the same time, we are going to move this. So double bond, double bond, double bond, three double bond. So this is the resonating structure of benzaldehyde. Now tell me, if there is an electrophile, on which position this electrophile will attack? Ortho, para, meta. What do you think? Please answer me. Meta. It will attack on meta because this electrophile, that means basically electron deficiency. This is having electron deficiency, and it will attack on that position which will have electron density high, which will have more electrons. So on ortho there is positive charge, that means it is facing deficiency of electron. On para it is also facing deficiency of electron, or ortho also facing deficiency of electron. So there is only one position that left, it will attack on meta. So this -M group will be acting as meta directing group. It will always allow this electrophile to attack on meta position. Please do let me know if you are having any issues with this. Can I change the slide? Can I change the slide? Adriel, Priyadarshini?
Yes, sir.
Okay. Now, the same thing I have written here. You can see that all plus N group for benzene ring for upcoming electron, plus N activating group. It is known as activating group because it gives electron to the benzene ring, and it is ortho-para directing. Ortho-para directing, and you can see all -M. Here I'm going to write directing, and all -M is deactivating, since it decreases electron density, and since it is decreases electron density, it is meta directing. -M acting as meta directing, plus M acting as ortho and para directing. Okay. Now see what is aromatic, non-aromatic, and anti-aromatic. So there are 4 rules which we need to follow, and any one of them will fail, then it is non-aromatic. Then it is non-aromatic. It is very important. There are 4 rules. If any one of them will fail, then it is non-aromatic. First of all, compound should be cyclic. That means any compound which is acyclic will be non-aromatic. Compound should be planar. Compound should be planar. That means each carbon, first of all, it should be cyclic and each carbon should be either sp or sp2. And then the third, compound should have complete conjugation. If it is cycle, closed ring, the conjugation will be complete in the cycle. That means the pi electron will move from each corner to every corner. And then comes the last rule, that is Huckel rule. So what does this Huckel rule say? Huckel rule has two formula, 4n plus 2 pi electron and 4n pi electron. If you are going to put n is equal to 0, you will get 2 pi electron. If you are going to put 1, you will get 6 pi electron and then 10 pi electron. And if you are going to put n is equal to 3, you will be getting 14 pi electron. So I'm going to take an example of this benzene. First, you need to check whether it is cyclic or not. It is cyclic. Then you are going to check the planarity. So each carbon here will have sp2 hybridization, trigonal planar. It is planar. Then you are going to check whether the conjugation in the complete cyclic or not. Yes, complete cycle. Now then count the number of pi electron. Number of pi electron is basically the electron due to pi bond. So there are 3 pi bond. That means 3 into 2, 6 pi electron. 6 pi electron. And here you can see 6 pi electron. Each and all of these 4 satisfy. That's why this benzene is aromatic. This benzene is aromatic. How we checked it? Cyclic, yes. Planar, yes. Complete conjugation, yes. 4n plus 2 pi electron. 4n plus 2 pi electron, yes. That's why it is aromatic. Now I'm going to show this. For this is your for anti-aromatic. So I'm going to take an example of this. Now you can see cyclic, yes. Planar, you can see each carbon having sp2, yes. Complete conjugation, yes. Now pi electron, for n is equal to 1, you can see 4 pi electron. For n is equal to 2, 8 pi electron. That means it is table of 4. It is table of 4, 12 pi electron. So you can see here 4 pi electron is there because 2 pi bond, that means 4 pi electron. That's why this compound is anti-aromatic. If any one of the 4 and if any one of the 4 will fail, then it is anti-aromatic. Is that clear? Please do tell me, is that clear?
Yes, sir.
Can I change the slide?
So can you explain anti-aromatic again?
Anti-aromatic. See, you have 4 conditions. The first one is should be cyclic. Anti-aromatic and aromatic are same for the 3 rules: cyclic, planarity, conjugation. This is in conjugation. You can see it will move to this pi sigma. This is in conjugation. Fourth rule is the Huckel rule. If it will have if its pi electron will follow this, then it is aromatic. If this pi electron will follow this, then it is not anti-aromatic. Are you getting my point? This is cyclic, this is planar, this is in full conjugation, complete conjugation. And you can see 2 pi bond, that means one bond has 2 electrons. So 2 pi bond will have 4 pi electron, and 4 pi electron comes in anti-aromatic. Adrian?
Okay, yes, sir. Thank you.
Okay. Can I change the slide? This part is for homework. You can see this is your anti-aromatic. Why it is anti-aromatic? The rule is failed. The first rule is failed. That's why it is anti-aromatic. So this part is for homework. Okay. So first of all, if I'm going to extract a PDF from here, you need to study about this whole. There are some questions that I am giving you for homework. So you need to do it at home. Can I change the slide? Adriel, Hamza, Priyadarshini, please do respond.
Yes.
Now see, there is hyperconjugation, which has another name, no sigma bond resonance. What's its name? No sigma bond resonance or Baker-Nathan effect. It has three names. The first one is hyperconjugation, another one is no sigma bond resonance, and then Baker-Nathan effect. Now you can see this inductive effect is partial displacement of sigma electron, but here complete transfer of sigma bond electron takes place. That is hyperconjugation. Complete transfer of pi electron, resonance. Complete transfer of sigma electron, that is hyperconjugation. And partial displacement of sigma electron, that is inductive effect. Only applicable to cation, carbocation, carbon free radical, alkene, alkyne, phenyl system. Only applicable to this, not carbon anion. You need to remember this. This hyperconjugation is not for carbon anion. It is for carbon carbocation. It is for carbon free radical. It is for alkene. It is for alkyne. It is for phenyl. Is that clear? And there should be alpha hydrogen required with respect to this carbocation, carbon free radical, alkene, alkyne, and then what is this? And then phenyl. Okay. So you can see how we calculate alpha hydrogen. So this is your system. This is your system. You can see. Okay, wait a minute. It does not move. Okay. This is your system. This is your alkene. The number of carbon which is directly the carbon which is directly attached with this alkene, carbocation, any of this system is alpha carbon, alpha carbon, alpha carbon, and alpha carbon. And the hydrogen which is directly attached with this carbon is known as alpha hydrogen. So you can see this will have 9 alpha hydrogen, because you can see this carbon is making only one bond. So 3 more bonds that is satisfied by hydrogen. So each alpha carbon is having 3 alpha hydrogen. So total alpha hydrogen is 9 alpha hydrogen. Is that clear? The carbon which are directly attached with this system, carbocation, carbon free radical, alkene, alkyne, and phenyl. You can see this is your carbocation. So this is also your alpha carbon, alpha carbon, alpha carbon. So 9 alpha hydrogen is there. Now you can see this is your free radical. So this is your alpha carbon, alpha carbon, alpha carbon. So 9 alpha hydrogen. Now this is your system, phenyl. So this is your alpha carbon. So it has 3 alpha hydrogen. Now you can see this is your system, which has alpha carbon, alpha carbon, alpha carbon, 3 alpha carbon, 9 alpha hydrogen. Now this is your system. You can see alpha carbon. 2 carbon is directly attached with this radical. So 2 alpha carbon and 2 hydrogen, 2 alpha hydrogen here and 3 alpha hydrogen here. There is total alpha hydrogen, that is 5 alpha hydrogen. With respect to this is alpha carbon, and this has total 6 alpha hydrogen. This is how we calculate alpha hydrogen, and this alpha hydrogen is very important in our syllabus, because stability is directly proportional to the alpha hydrogen. Stability of carbocation, stability of free radical, stability of alkene, stability of alkyne, stability of phenyl, that is directly proportional to alpha hydrogen. The compound similar to this or same like this, which is having more alpha hydrogen, will be more stable. Is that clear?
Yes, sir.
Can I change the slide?
Yes.
Oh. Now you can see. You can also see there is no alpha carbon, 0 alpha carbon. That's why 0 alpha hydrogen, because this free radical is not connected with any carbon, which is called alpha carbon. This is 0 alpha carbon, 0 alpha hydrogen. Stability is directly proportional to number of alpha hydrogens. We give preference to resonance first in stability and hyperconjugation and then inductive effect. We give preference in this way. Is that clear? Clear. Now, stability of alkene directly proportional. Am I audible to both of you or all of you?
Yeah, sir.
Oh, am I audible? Again, I disconnected. Wait a minute, please. Okay. My screen is visible to all of you. A, B, C.
Yes, sir.
Can anyone tell me which one is more stable in this A, B, C? You just need to count the number of alpha hydrogen and you will be able to tell me the answer. A is the most stable. Oh, no, this is. Adriel, did you send the text in this right now? Did you send it right now? B is the most stable. Okay. Let me explain. This is your alkene system. There is alpha carbon, alpha carbon, alpha carbon. And each alpha carbon has 3 hydrogens, so 9 alpha hydrogens. Then comes this is your system. So this is your only alpha carbon, 1 alpha hydrogen is there. This is your system, which is having 2 alpha carbon is here, and alpha carbon is here. This alpha carbon, 2 alpha hydrogen, 3 alpha hydrogen, 5 alpha hydrogen. So the most stable is A, then C, then B. Are you able to understand this alpha carbon? Yes or no? The carbon which is directly connected to the system. The system means carbocation, carbon free radical, alkene, alkyne, phenyl. Is that clear?
Yes, sir.
Now see, if you are going to check this is your alkene, this is your alpha carbon. So it will have 6 alpha hydrogen. This is your system. So this is your alpha carbon, and this is also your alpha carbon, and this is your 6 alpha hydrogen. But in this case, B will be more stable than this because you know that this is your cis and this is your trans. So there will be a repulsion between this group since both are bulky and on the same side. So that's why this trans will be more stable than the cis. Is that clear? What about this one? Can anyone tell me? See, this is in conjugation. That means resonance is there as well as hyperconjugation is also there. Only there is hyperconjugation. So we give preference to resonance. That's why this is more. So it's very easy, I think. Right? Yes or no?
Yes, sir.
Okay. Can I change the slide?
Yes, sir.
Okay. Now see, I'm going to tell you about the bond length. Bond length. So you can see what is bond length. You know that triple bond having shorter bond length, and then comes double bond, and then comes single. That means single bond is the lengthiest bond or the lengthy bond. But there is another condition. Single is more lengthy than partial double bond character. Partial double bond. Then comes your pure double bond. Pure double bond. And then comes your triple bond. See, how does this partial double bond come? So basically, it is due to the resonance. So due to resonance, a single bond will have partial double bond character. And that partial double bond character will be lengthy than the pure double bond character. Is that clear? Is that clear, everyone? Can I change the slide?
Yes, sir.
The next point I want to tell you is about acid and base. Acidic character. Wait a minute. First of all, we are going to talk about Lewis acid and Lewis base. Lewis acid, Lewis base. What is Lewis acid? You have studied this in previous classes. Lewis acid is the one which is electron pair acceptor. Electron pair acceptor. And Lewis base is the one which is electron pair donor. Electron pair donor. Electron pair donor. So the one which donates electron is called Lewis base, and the one which accepts electron is called Lewis acid. Oh, wait a minute. Ma'am, I will just take 2 to 3 minutes more. Okay, thank you. Now see, acidic character, that means the group which will take electron or which will withdraw electron. So acidic character is directly proportional to minus I, which is directly proportional to minus R, which is directly proportional to Ka, that is acid dissociation constant, which is inversely proportional to plus I, and which is inversely proportional to plus R, or plus M you can say, or minus R or minus M. So a compound which will have more group which withdraw electron is not will be more acidic. Are you getting my point? The compound which will have more withdrawing power, or the group which has more withdrawing power, that is more acidic. And basic character is directly proportional to the donating one. Directly proportional to Kb as well, inversely proportional to pKb, inversely proportional to withdrawing group, inversely proportional to withdrawing group. Is that clear? You have seen in class 12 carboxylic acid, the group which have more withdrawing group will have the compound which will have more withdrawing group will have more acidic, will be more acidic. Is that clear? Please do write
Yes,
it.
sir.
And there is a power cut off in my area, so I will be sending you this PDF. I will also write some questions in this, and you will be getting with all this, whatever I have written here, and I will add more questions. And tomorrow we are going to start aromatic compound. And for aromatic compound, it is very important to note the resonance. So please do revise. You have very less time left, so you need to be serious, and whatever I teach here,